Image segmentation. A central problem in image processing is the segmentation of an image into various coherent regions. For example, you may have an image representing a picture of three people standing in front of a complex background scene. A natural but different goal is to identify each of the three people as coherent objects in the scene. The problem, one of the most basic problems, to be considered along these lines is that of foreground-background segmentation. We wish to label each pixel in an image as belonging to either the foreground of the scene or the background. It turns out that a very natural model here leads to a problem that can be solved efficiently by a minimal cut computation. Let V be the set of pixels in the underlying image that we are analyzing. We will declare certain pairs of pixels to be neighbors and use E to denote the set of all pairs of neighboring pixels. In this way, we obtain an undirected graph G equals to VE. We will be deliberately vague on what exactly we mean by a pixel or what we mean by the neighbor relation. In fact, any graph G will yield an efficiently solvable problem, so we are free to define these notions in any way that we want. Of course, it is natural to picture the pixels as constituting a grid of dots and the neighbors of a pixel to be those that are directly adjacent to it in this grid, as shown in figure 7.18a. For each pixel I, we have a likelihood AI that it belongs to the foreground and a likelihood BI that it belongs to the background. For our purposes, we will assume that these likelihood values are arbitrary non-negative numbers provided as part of the problem, and that they specify how desirable it is to have pixel I in the background or foreground. Beyond this, it is not crucial precisely what physical properties of the image they are measuring, or how they were determined. In isolation, we would want to label pixel I as belonging to the foreground if AI is greater than BI, and to the background otherwise. Otherwise, however, decisions that we make about the neighbors of I should affect our decision about I. If many of I's neighbors are labeled background, for example, we should be more inclined to label I as background too. This makes the labeling smoother by minimizing the amount of foreground-background boundary. Thus, for each pair ij of neighboring pixels, there is a separation penalty pij greater than or equals to 0 for placing one of I or j in the foreground and the other in the background. We cannot specify our segmentation problem precisely in terms of the likelihood and separation parameters. It is to find a partition of the set of pixels into sets A and B, foreground and background, respectively, so as to maximize Q of AB, which is equals to the summations of AI summing for all I in A, plus the summations of Bj summing for all j in B, minus the summations of Pij summing for all ij pair in E, such that the size of A intersect the pair ij is equals to 1. Thus, we are rewarded for having high likelihood values and penalized for having neighboring pairs ij with one pixel in A and the other in B. The problem then is to compute an optimal labeling, a partition AB that maximizes Q of AB. Designing and analyzing the algorithm. We noticed right away that there is clearly a resemblance between the minima cut problem and the problem of finding an optimal labeling. However, there are a few significant differences. First, we are seeking to maximize an objective function rather than minimizing one. Second, there is no source and sink in the labeling problem, and moreover, we need to deal with values AI and BI on the nodes. Third, we have an undirected graph G, whereas for the minimal cut problem, we want to work with a directed graph. Let's address this problem in order. We deal with the fact that our segmentation problem is a maximization problem through the following observation. Let Q equals to the summations of AI plus BI summing for all index I. The summations of AI summing for all index I in A plus the summations of Bj summing for all j in B is the same as the sum Q minus the summations of Bi summing for all I in A minus the summations of Aj summing for all j in B. So we can write that Q of AB is equals to capital Q minus the summations of BI summing for all I in A minus the summations of AJ summing for all j in B minus the summations of Pij summing for all ij in E, such that the size of A intersect ij pair is equals to 1. Thus, we see that the maximization of Q of AB is the same problem as the minimization of the quantity. That is, Q prime of AB is equals to the summations of BI summing for all I in A plus the summations of AJ summing for all j in B plus the summations of Pij summing for all pair ij in E, such that the A intersect the set ij is equals to 1. As for the missing source and the sink, we work by analogy with our constructions in previous sections. We create a new supersource S to represent the foreground and a new supersink T to represent the background. This also gives us a way to deal with the value AI and BI that reside at the nodes. Whereas minima cuts can only handle numbers associated with agencies. Specifically, we will attach each of S and T to every pixel, and use AI and BI to define appropriate capacities on the agencies between pixel I and the source and the sink respectively. Finally, to take care of the undirected agencies, we model each neighboring pair ij with two directed agencies, ij and ji, as we did in the undirected disjoint paths problem. We will see that this works very well here too, since in any ST cut, at most one of these two oppositely directed agencies can cross from the S side to the T side of the cut, for if one does, then the other must go from the T side to the S side. Specifically, we define the following flow network G prime equals to V prime E prime, shown in figure 7.18b. The node set V prime consists of the set V of pixels together with the two additional nodes S and T. For each neighboring pair of pixels I and j, we add directed agencies ij and ji, each with a capacity Pij. For each pixel I, we add an edge Si with a capacity Ai and an edge It with a capacity Bi. Now an SD cut AB corresponds to a partition of the pixels into sets A and B. Let's consider how the capacity of the cut C of AB relates to the quantity Q prime of AB that we are trying to minimize. We can group the agencies that cross the cut AB into three natural categories. Agencies Sj, where j is in B, this H contributes Aj to the capacity of the cut. Agencies It, where I is in A, this H contributes Bi to the capacity of the cut. Agencies Ij, where I is in A and j is in B, this H contributing Pij to the capacity of the cut. Figure 7.19 illustrates what each of these three kinds of agencies looks like relative to a cut on an example with 4 pixels. If we add up the contributions of these three kinds of agencies, we get C of AB equals to the summations of BI summing for all I in A plus the summations of AJ summing for all j in B plus the summations of Pij summing for all ij in E, such that the size of A intersect the pair ij is equals to 1, where the summations of all three terms is equals to Q prime of AB. So everything fits together